Hi, this video is the project turning tree for heat and mass transfer. Question 1 is learning objective 8A and 7T, heat transfer unit operation and condensation. So we have a water vapor condenser that has a 144 branch of pipes with outer diameter of 5 centimeters, and it's arranged in a 12 in 12 square. And the pipe exposed the saturated water vapor at a pressure of 30 kilopascal and the surface temperature of 25 degrees. And the goal is to calculate the rate of steam condensate per unit length of pipe set. Here is the schematic of the question. We assume it's a steady state and the properties is constant and no change in kinetic and potential energy. So I found at 30 kilopascal saturated vapor steam properties and saturated liquid at TF 321 Kelvin from table A9. We calculate H prime Fg from the formula, and also we calculate H, and from here we can calculate the Q from one tube and multiply it by the 12 to get the total Q, and the condensation rate is the Q total divided by H prime Fg. So that's question 1. Question 2 include learning objective 4A, 4B, and 5C. It's a 0-dimensional, 1-dimensional, heat transient, and spherical coordinate. So there's two parts on it. On part A, there's a steel shaft with diameter of 0.11 meters that placed in gas furnace with temperature of 1200 and displacement coefficient of 100 watt meter square Kelvin. If the initial temperature is 300 Kelvin, how long does it take the center temperature to reach 800 Kelvin? So I calculate the Biot number, and it's smaller than 0.2, so we can do lamp analysis, and from the formula we can find the time that it takes to get to that temperature. On part B, we have one-dimensional, so we have a spherical apple with given all the specification, and we have the temperature of center of the apple and surface temperature of the apple and the amount of heat transfer after 1 hour. So it's all the information that the question gave us. So I calculate the Fourier's number, the Biot number, and you can see it's greater than 0.2. So we go table and read the gamma and like C values and calculate the theta because it's a spherical coordinate. And as you can see, we can get the temperature on the center, on the surface, and also at the bottom the amount of heat transfer. Question 3, including learning objective 4C and 5B. It's a multi-dimensional heat transient and is in cylindrical coordinate. So I have a cylinder that 15 centimeter tall, 8 centimeter diameter, and air is flow on it at 20 degrees. So we want to get the temperature of the center of the cylinder and the temperature of the center of the base and heat loss Q after 15 minutes. So it's a multi-dimensional heat transient. We get the information from table A15, the air properties, calculate alpha Fourier's number, and use the cylindrical coordinates formula to get the temperature at the center of the cylinder and on part B we get the temperature at the center of the base of the cylinder, and on part C from that formula we used to find the heat lost Q. Question 4. Include learning objective 1B, 7A, 7B, and 7C. So it's convection, internal and external force, and natural convection. So in that figure, we have the electronic chips that the temperature of in is 85 Fahrenheit and the flow rate of 22, and the outlet temperature is 100. We want to find the surface temperature of the pipe. We assume that thermal resistance of the pipe is negligible. So the heat is a combination of forced convection and natural convection in this question. So I have the forced convection formula and natural convection formula. We get the average temperature and find the properties. They are constant, and we can calculate the forced convection and natural convection. So that's a try and error type question. So I guess the surface temperature is 150, and I go find a T film 115, get the information and put it on the formulas, get radial and get Nusselt, and get the age and area, and we come back and put it on that star formula to find the TS. So with the first case of 150, we did all of those, and we come back and put the numbers, and we get TS 149.9. So our guess was so close enough to 150. So 150 is surface temperature. I add a second part to this question, and that is, how about if T out was unknown instead of T surface? So again, we do a mass and energy balance here. It's natural convection, free convection. So I have the formulas here, and we have to use the delta T log mean. And from forced convection inside the tube, we calculate H in, Nusselt in, H out, and Nusselt out, and this one. And for external forces, T film is the average T. Again, it's a try and error. I didn't run that in the paper, I run it in the computers, and that's the result I get. The T surface 80.8 and the out temperature is 85.4. That was question 4. Question 5 is learning objective 6B, is the transient mass transfer. So there is a thick wall made out of the rubber and exposed to pure oxygen gas on one side, and we assume both wall and oxygen gas are isothermal at 25, and oxygen concentration at wall surface is constant. We are looking for time that's required to oxygen concentration at x equals 5 millimeters to reach 5% of its concentration at the wall surface. So the DAB is given in the problem, and from this formula, CA at the interface is 0, so CAX T divided by CAX is ERFC of 5 times 10 to negative 3 divided by 2 square root of DAB times time. And we solve that from the error function at 0.05, and we keep going to find out the time, and it's about 4 hours and 4.3 hours. And the last question, question 6, is covering learning objective 8b, the mass transfer unit operation, that I have a membrane unit that is a rubber membrane and separating carbon dioxide gas, which maintained on one side at 2 atmosphere and the other side as 1 atmosphere, and temperature we assume is constant at 25, and we want to determine the molar density of carbon dioxide inside and outside of the membrane on both sides. So the molar density is solubility of CO2 times the partial pressure. We get the partial pressure and change it to the bar unit, and also get the solubility from the tables. And from this formula we calculate the both side molar density. The amount of molar density of carbon dioxide outside the rubber membrane remain the same as above calculation, because a very small amount of CO2 diffuse into rubber membrane, and also it depends on its porosity of the rubber membrane. Thank you so much.